random quotes.
All right, so today we're going to be doing 4.3a, which is connecting the first, second, and third derivative graphs and how they basically make and help us understand different aspects of functions. So we have something called the first derivative test. Today you're going to be learning the first derivative test, and we use it to find maximums and minimums, both local and absolute. So we call these extrema, and we're also looking at increase and decrease intervals of the function. So as you can see, this one here is a local max because we have an absolute max that's larger than it over this particular interval from A to B. What you're going to notice is some local maxes and mins, they have derivatives that are 0 because they flatten out. But then we have absolute maxes and mins that can be a cusp or corner. And the thing that we have to understand is that not all absolute maxes or mins occur when the derivative is 0, because can you even take the derivative here at all?
No.
No, but we could technically take the derivative up to that point, right? Leading up to that point. And the derivative would be what? Increasing up to that point. And then from here, the derivative would be?
Decreasing.
Yeah, the slope being positive and negative, okay? So we can help determine where these absolute maxes and min occur when the derivative changes from positive to negative or negative to positive. All right. So we're going to talk a little bit about how we can determine that. I forgot to erase this one. So what you're going to do is you're going to create these number lines. In the middle of the number lines, you're going to have whatever the x value is that you determine when you set your derivative equal to 0, okay? And you're going to look at both sides of the graph, either graphically or mathematically. So what do you notice about the derivative here on the left? Is it positive or negative?
Positive.
Positive. What about on the left?
Negative.
I'm sorry, on the right.
Negative.
Negative, good. So, I know. So as you can see, if we determine this is positive and this is negative, we know that C is a local maximum, okay? Additionally, something like this where we can't necessarily determine the derivative at that maximum point, we can still look at the derivative on the left and right and help us determine if it's a local max or min. So on the right, as you can see, the derivative is positive, and on the right it is negative. So the main idea here to understand is if we go from positive to negative, we know that that point in the middle is a maximum, okay? Either absolute or local, we don't know yet.
Indeed.
All right, so for the next one, we have our point in the middle, okay? And if you look at the slope on the left, is it negative? Good.
It is negative.
And then the slope on the right
Positive.
is positive. So when it's negative to positive, you know that that point in the middle is going to be a minimum. And the same thing over here, even though the derivative cannot be found at that point, it starts negative on the left and then it ends positive on the right.
Mm-hmm.
So when we go from negative to positive, you know that that point is at least a relative minimum. So we're also going to have other situations where we can determine something is an inflection point or a critical point, but it's not giving us any data. So this may come up because we might find the derivative is 0 there, but what you can see is the derivative doesn't change. It's still positive on both sides. Brandon, I think you're going to annoy everybody on this video, so maybe, don't do that. All right. And on this side over here, even though they have different slopes, they're both negative. So the main idea is if we go from positive to negative, relative max, negative to positive, relative min, and if you don't change, it's no extreme. All right, here are the steps to finding using the first derivative test. Basically, you have to find the critical values, critical x values. You guys just did that on the last test. You're going to take the derivative and set it equal to 0. You've been doing that. Then you're going to find the values for which the derivative is undefined. So you're looking for cusps and corners and vertical tangents, which we're looking for. You guys know how to find that now because we've been practicing it. Now here's where things get a little bit different from what you've already learned. You're also going to have to create a sign chart to test the intervals. So that's what we're going to be doing today that's completely new. And then you're going to have to plug back into the derivative. So the main thing here that people often forget is you have to plug those values back into the derivative, not the original function, so not to confuse the two. All right, step 1, we have a graph of this, but we're going to start by taking the derivative of the function. So what would be the derivative of this function?
12x to the third.
Good. 12x to the third.
Minus 12x to the second.
Good.
Minus 24x.
Minus 24x. Good.
That's it.
That's it. So we're going to set this equal to 0, and then we're going to solve for x. So I see that I can take out a GCF. Yeah.
I'm gonna ask you to factor that out.
Yep, that's what we're going to do.
Take out a 12.
So anytime you have something like this, you have to solve it. So to solve it, you're just going to use any solving methods you know. So we're going to factor out a 12x. And we're left with this. And then we're going to be able to factor it one more time, right? So what are factors of -2 that would add up to -1?
-1, -1.
-2 and +1 would multiply to give me -2 but add up to a -1. So then you're going to set each of these equal to 0. Oops, I don't know why I did that.
12 equals 0? Or
Not correct. So you're going to set 12x equal to 0. You're going to set x plus 1 equal to 0. And x minus 2 equal to 0. And then you're just going to solve each one of these equations. So we get x equals 0. We get x equals -1. And we get x equals 2. Now these right here are our critical points. So what you're now going to do is you're going to create a number line. And on that number line, you're going to place these values in chronological order, like so. Doesn't matter if they're equally spaced or anything like that. And now what we're going to do is we're going to have to test the in-betweens. So what I mean by that is you're going to have to find points that exist in between here to plug back into the derivative. Now, when you plug back into the derivative, you can use the pre-factored or the factored version. Factored version is usually going to be a little bit easier to deal with, so that's what I'm going to do. All we have to do is determine if that value is going to be negative or positive. You don't have to actually solve to get a number. So, what's a number we could plug in over here? -2. So, I'm just going to plug -2 into my factored version. And then I'm going to evaluate if that number is going to be negative or positive. So right here, what's the product of a negative and a positive? A negative, right? What's the sum of -2 and 1? Is that positive or negative?
Negative.
Negative. And lastly, what's a negative minus another negative?
Negative.
Negative. So what's the product of 3 negative numbers?
A negative.
A negative. So we know that no matter what we plug in here, it's going to give me a negative value. Okay? So you can actually solve it to get a number if you feel more comfortable with that and just determine if that number is negative or positive, or you can just do it that way.
Oh, so you don't like solve it? You
No.
Just look at the x's.
If it's going to be a positive or a negative. We don't care what the number is, we only care if it's negative or positive.
Okay.
So the next one, we're going to have to plug something in between -1 and 0. So what could we plug in?
0.5.
Negative
Or
0.5. So I'm going to plug negative 0.5 in. And if you don't like doing like the testing, you know, without the numbers, you can just actually solve it. That will still work as well if you feel better about that. So a negative times a positive is going to be
Negative.
negative. A smaller negative number plus a bigger positive number is going to be
Positive.
good. And then a negative minus a negative is always going to be.
Negative.
So what's the product of 2 negatives and a positive?
Negative? No, positive.
What's a negative times a negative?
Positive.
Positive times a positive is still a positive.
Positive. Yeah.
And then we're going to plug in a number between 0 and 1, or 0 and 2, which is going to be 1. So we're plugging in 1. So with 1, I get a positive, positive, and then a negative. What's the product of 2 positives?
Positive.
Times a negative is?
Negative.
Negative. And then we're going to plug in a number bigger than 2, which is what?
3.
3. So remember, you can pick any number you want that falls in that interval. So we get a positive, 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 so that number is going to be positive.
Hey, look, it looks like the graph.
Wait, for -0.05, how did you get positive?
Because this right here is going to become -6 times 0.5 times this is going to be -2.5. So if you multiply these 3 numbers together, that's going to give you a positive number. So yeah, the whole point of this is now we can determine if these values are max, mins, or neither. So from here we go negative slope to positive slope. So is this a minimum or a maximum?
Minimum.
A minimum. From here we go positive to negative, which means that 0 is a
Max.
maximum. And then here we go negative to positive, which means 2 is a minimum. So the visual for this, at -1 on the graph, you can see, and at 2, do you see how those are both minimums?
Mm-hmm.
And then do you see here at 0 how that's a local maximum?
Yeah.
So the graph matches the expectation.
It makes sense.
Makes sense. Okay. So I'll just forewarn you. The next one, the algebra can be a little bit difficult. So I'll kind of show you like how to do it, how to go about it, and then at the end I'll talk about the easier way to approach it. So we're looking at this one here. Right off the bat, even if you didn't have the picture, you know that this graph has what?
A corner.
It has a cusp or corner, right? How did we know that it has a cusp or corner?
Odd over even.
Even
I'm
over
looking
odd.
at the graph.
Without looking at the graph. So,
Odd over even.
so what you're going to do to figure out where that cusp or corner occurs, you're going to take whatever is to that power, and you're going to set that equal to 0. Okay? And when you do that, you get t equals what? 6. So we know that that's going to be one of our critical points on our number line. But in addition to that, you're going to notice on the graph, there's going to be another value which acts as a critical point, but we have to find that by taking the derivative because that's where my derivative is 0. Okay? So how would I take the derivative of something like this? I'm going to have to use what rule?
The chain rule.
Well, we're going to have to use the chain rule, but we're also going to have to use the product rule, right? So
Because
the
t is multiplied by
exactly.
6 times.
So we have f of t, which we're going to call t. And what would be f prime of t?
1.
1. And then we have g of t, which is this. And then we're going to take the derivative of g of t, which here you're going to use the chain rule. So the 2/3 is going to come out front. It's going to be 6 minus t to the power of -1/3 times, what's the derivative of the inside here?
-1.
-1. So we're just going to use the product rule. So the product rule says I do f of t times g prime of t. So I'm just going to simplify it for you. It's just going to be -2t over 3 times 6 minus t to the positive 1/3 power. So just to clarify what I did here, the 2 stays on the top, the -1 stays on the top, and the t all go on the top.
Uh-huh.
What's on the bottom is the denominator, which is the 3, and then why did I bring this down to the denominator?
To make the exponent positive.
To make the exponent positive, good. And that's going to be plus the product of the derivative of f times regular g, which is just going to be this, because it's just 1.
Yep.
You're going to set this equal to 0. And then you're going to try to get one of the fractions or the numbers to one side so you can cross multiply. So I'm going to add this one over because it's already negative. So I have this equals this. That's a negative sign. It just kind of got like merged with the t. Right here. Alright, so now that we're here, we can put this over 1, and now we can cross multiply. So this gives me 2t equals 3 times. Now here's where we have to kind of use our knowledge of algebra. What do you notice about the base of both of these things that have the exponent to them? They're the same,
They're the
right?
same.
Yeah, what's up, Jacob?
I figured it out.
Okay. So yeah, the base is the same. So what do we do with these exponents? Anytime you have the same base.
Subtract.
What would you do if I told you to multiply x
You add them.
squared? Yes.
Okay.
X squared times x to the 5th. You would tell me it's x to the 7th, right?
Mm-hmm.
That's the same idea here. You have the same base, and you're adding the powers because you're multiplying them. So what would be 2/3 plus 1/3?
3/3.
Which is just 1.
Exactly, 3/3, which is just 1. So when you multiply these together, the fractions are just going to become 1 when you add those exponents. Is everybody good with how we got that?
Yup.
Now from here, it should be pretty easy to solve. We can just distribute the 3. And then I'm going to add the 3t to both sides, which gives me 5t equals 18.
Ew.
So t equals 3.6. So not too bad. So everybody see how we got that? Alright, so we know that we have 2 critical points. Now we have to put those on our number line. So you're going to make a number line, and it's going to have 3.6 on it, and regular 6 on it. And then we're going to have to plug in points. So remember, we're going to have to plug points into this. So we don't really want to have to plug in numbers completely. It's going to be difficult. So I'll show you the easiest numbers we can pick. What's going to be the easiest number to plug in less than 3.6?
3.
0.
0.
Oh yeah, 0.
So if we plug in 0, we get negative 2 times 0, which is what?
0.
0. So this whole thing goes to 0. So this doesn't even matter anymore. When we plug in 0 over here, what's 6 minus 0? Yeah, 6 to the 2/3 power. Do I really care what it is?
No.
As long as it's what?
Positive.
Which it is. So we know that this is positive. Now we're going to plug some number in between 3.6 and 6. I'm thinking we plug in 5. And the reason for that is I know that 6 minus 5 is 1. And then anything 1 to any power is just 1. So that's going to be the easiest one to work with. So if I plug in 1 here, I get negative 2 over, because I multiply negative 2 by 1, over 3 times 1, which is going to come out to be what kind of number?
Negative.
Negative. It's going to be negative 2/3, or 2/3.
Is it your T5?
Yes.
So negative 2 times 5 is not 2.
6 minus 5.
No, the numerator.
Oh, you're right. Thank you.
Am I bugging out? Or?
No, you were right. You were right 100%. I don't know. I was thinking
No, it's because you said 1 in the
I know.
denominator, so you thought you were plugging in 1 for 2
Yeah,
and you were doing that.
that was my mistake. Yeah, you're right. It's negative 10 over
You're
3. And then here, this is going to be 1.
To any number.
So 1.
Yep.
So negative 10 over 3 plus 1. What is negative 10 over 3 is approximately negative 3.3 plus 1. Is that going to be positive or negative?
Negative.
Negative, because the bigger number is negative, right?
Yep.
And then the last one is a little bit more tricky, because we're trying to find something that's going to work, that's bigger than this, that has a perfect third root. So
8.
I think we can do 6 minus something is going to give me negative 27. So 6 minus what is going to give me negative 27? Let's see. 33? Yeah, 33.
There's
So
no way you think that we would use 33.
well, no, you could, if you wanted to in the calculator, just plug any number in. It's going to come out messy, but at least it will work, right?
Yeah.
But the reason I'd plug in 33 is because 6 minus 33 is negative 27, which is a perfect third root. So we get negative 54 over 3 times negative 27. The third root of that is negative 3. So that's going to come out to be positive.
Yeah, negative over negative.
Positive. And it kind of matters the size here, because depending on how big it is and how positive it is. So this one actually divides nicely. Divided by 9, that's going to be 6. So the first term comes out to be 6 when I plug in negative 27. And over here, if I plug in, or 33, regular 33, I get the third root, or this 2/3. So I put it to that power. It doesn't work. Hang on. So this is going to come out to be a positive number as well. I think it's positive 9. So what's a positive plus a positive?
Positive.
A positive. Now, I wouldn't expect you to be able to figure out to plug in 27, but you could just plug in any number you want and put this all into the calculator. But I probably wouldn't give you one this difficult on a test, okay?
Okay.
So if you look at our picture over here, does it match what we have?
Yeah, yes.
Yeah, so see how here it's increasing,
Decrease.
then decreasing, which makes this value a what?
A max.
A max. And then here it's decreasing and then increasing, which makes this
Minimum.
a minimum, just like the graph. So yeah, this one's a little bit tricky for the last part. So as long as you understood the process, most of the ones you're going to do are polynomials, like the first one. All right, I'll go ahead and hand out your homework.